This Mechanics 1 video details resultant velocities where a non-right-angled triangle needs to be set up. So our aims for this video are to set up non-right-angled triangles for resultant velocity problems, and to be able to use the sine rule or the cosine rule to help us find the unknown values that we require. So these are the sine rule and the cosine rule. The sine rule as a over sine a equals b over sine b equals c over sine c is a rule that you need to learn. You can also use all of those fractions upside down and it will still work just as well. The other rule is the cosine rule, which is a squared equals b squared plus c squared minus 2bc cos a. That is actually given to you in the core section of the formula booklet. So you do not need to memorise this, but you do need to be able to use it. You do need to be careful how you set labelling the triangle. We use capital letters for the vertices, so we could call one corner A, one corner B, and one corner C, and the lowercase letters are for the opposite side. So we'd have lowercase a opposite A, lowercase b opposite B, and lowercase c opposite C. So if we tried to solve a problem where a non-right-angled triangle is involved, for this problem we've been given a plane that has an airspeed of 250 km per hour, has to fly from town A to town B, which is 100 km due east of town A. The wind is blowing from 030 degrees at 50 km per hour. So first of all, I'm going to sketch a velocity triangle. We just consider our compass directions first. North, south, east, west. So we've got town A positioned here, and draw town B somewhere to the east. And that vector will actually be our resultant velocity. If we try and mark on now the wind speed is from 030. So 030 would be something like this. It's going from that direction, so it's actually going to travel that way. So that would be our wind speed of 50. So the plane must actually try to travel in this direction to complete our vector triangle. So wind at 50, plane relative speed of 250 in that direction, and A to B would be our resultant speed. So that's our vector triangle. Part B has asked us to consider the direction that the plane is heading in. So we should aim to give this as a bearing. So we need to consider the angles in our diagram. And we actually do know one of the angles in our diagram. So if we add a vertical and extend this on, the angle there would be 30 degrees. This is the bearing of the wind. So that means that this angle here must be 30 degrees. The other angle in there is a right angle, which is 90. So in our triangle, this angle here must be 120 degrees. So we know one angle, one and two sides. And we want to work out the bearing, which is another angle. So we actually use the sine rule. The sine rule we can use to help us work out this angle in the triangle, work out angle B. So we can consider that sine A over A is equal sine B over B. We substitute in the values to that. Sine of 120 over 250 must equal sine of B over 50. Now I've chosen to set it up with the sine on the top and the side on the bottom because we've got an unknown angle. It just makes the rearrangement slightly easier to deal with. So if we rearrange that, we can come out with a value for sine B. So sine b is going to be sine 120 multiplied by 50, then divide by 250. We can just use a calculator to work it out, and that gives you that sine b is equal to 0.173. We round it, it does carry on further than that. So to work out angle B, we need to do 10 to the minus 1 of 0.173, which gives us an answer of 9.97 degrees. 233 degrees. It's important to make sure you calculate this in degrees mode, to make sure it calculates your angle in degrees. It's important as well to try and use the unrounded angle when you are working with the calculator until we get to a final solution. So for the next bit of the question, I will try and use the unrounded answer to 9.97. That has given us this angle in the triangle, and so this one here is 9.97. The one that's going to be most used to our direction, really, it's going to be the third angle in the triangle. To work out our third angle, we can just consider that the angles in the triangle must add up to make 180 degrees. So this must be 50.03. To add up to 180. If we do want to give us a bearing, that needs to be measured to north. So if we mark a north arrow in, we want the angle, which is the angle in the triangle plus this angle here. And the angle just marked on there would actually be the same as the 30 degrees up there, it's a corresponding angle. So our bearing would be equal to the 30 degrees plus this angle inside the triangle of 50.03 to give us a bearing of, we should write it as 0.80 degrees. Now we always put a leading zero if it's an angle less than 100 degrees, convention for bearings. We don't usually put decimal places on, but we could do if we needed to. So that's part B dealt with. Part C would like us to find out how long the flight will take. Because we've not been told anything about acceleration, we can consider speed as distance over time. We do know that the distance between the two places is 100 kilometres. We've been asked to work out the time, which means we need to know the speed. And the speed we want is the speed directly between A and B, which is going to be our resultant velocity. So again, we need to consider our triangle to work this out. So now we actually do know everything except the length of this side. We do know two of the sides and all three angles. So we could use the sine rule again, using the different pairs of results. For a bit of variety, I might try using the cosine rule, just to see what we come out with. You can just look this formula up. So the cosine rule is in the data sheet. So a squared equals b squared plus c squared minus 2bc sine a. So if this is the value we would like to find, I'll label it on V. The angle we're going to use in the formula is the one opposite that, so we're going to use the 50.03 degrees. So if I got a squared is going to be my v squared. B we can use as the 50. C is 250 minus 2 BC, so 2 times 50 is 250, and we're going to use cosine of 50.03 degrees. That will give us a value for v squared. So again, if you make sure you're in degrees mode on your calculator, but if you use that to work out a value for v squared, you should come out with 4.8938.6. And that's not an exact answer, so I'll put the point on the end. If we square root that, we come up by for v, which rounds to 221, and that will be measured in kilometres per hour as all the other ones were. So now we've got a value for v, we can actually calculate the time. So 221 must equal 100 t. So if we rearrange, it's going to give that t equals 100 divided by 221. If we calculate that, it will give us 0.452. That will be measured in hours. We could convert it to minutes if we wanted to by multiplying by 60, and that gives us about 27 minutes. Okay, thank you for listening.